changes in resting. So, these terms describe in relationship to the changes here in relation to the zero. Okay? So the first one's going to be called depolarization. DE, not DI. What does DE stand for? Deoxygenated. Reduced, right? So it's less than. Okay? So this we'll call as depolarization. In that direction. So for example, we're going from minus 70 millivolts say to minus 50. Okay, it's becoming less. Example from mine, so it's depolarization. Write it bigger. Becoming less negative, so it's going in that direction. Okay, that's depolarization. We talk about hypotonic, hypertonic. What's that prefix hypo mean? Low, and then hyper, high. So if we go more negative, it's called hyperpolarization. Example from minus 70 to minus 90 millivolts. Okay? We still use depolarization even if it goes beyond zero, by the way, just as a side note, because we'll talk about it. So it's becoming less negative is depolarization. It becomes more negative, it's hyperpolarization. Okay? So if I, good so far? If we open a sodium channel, will it cause depolarization or hyperpolarization? So to answer that, we need to know what the ion's charge is, which direction it moves. Sodium charge, positive 1. Which direction would sodium move? You open a channel in the plasma membrane. Into the cell. So if positive charges move in, will it go in this direction or in that direction? It becomes less negative because it's gaining more positive charges. Okay? How about you? Influx, inward flow of sodium. Okay? What if we open potassium channels? Why? Very good. Because it would move to the outside, we have more potassium inside, so it would leave the cell. They have positive charges, so losing more positive charges will cause hyperpolarization. Okay? Outward flux or efflux is called. What if we open calcium channels? What charge does calcium hold?
Negative.
Plus 2. Right, so plus 2 charge. Which direction does calcium want to move? Into it. But it's lower but still higher outside. Okay? It'll move into the cell. So will it cause depolarization or hyperpolarization? So what charge? plus 2, which direction is it moving? Into the cell. So cell was starting at minus 70. If it gains positive charges, what will happen? It becomes less negative, right? Because you're adding, you're going to neutralize some of that positive charge. What if we open chloride channels? Charge?
Negative.
Negative 1 charge. Which direction does chloride ions want to move? Into the higher on the outside. Okay? So if we gain negative charges, what will happen to the membrane potential? Becomes hyperpolarization. Efflux means leaving, influx coming into the cell. So what we need to know is what we need to do on the membrane, we need to know the charge and which direction it goes. And these are the 4 we need to recognize. Where do we have more sodium? Outside of the cell. Where do we have more chloride ions? Outside of the cell. Where do we have more potassium ions? Inside the cell. Where do we have more calcium ions? Outside the cell. Okay. This is how neurons, muscles, they react to these 4 ions. Which way are they going to go? So hyperpolarization becomes more negative, depolarization becomes less. Okay. So let's talk about the action potential. This is a conduction of nerve impulse. So this is the way our neurons communicate with other neurons and other cells, right? Whether it's muscle or glands. Okay. Signal does not decay. What that means is once produced, the same signal travels along. Okay. For example, pain, right? You may feel it here, but pain signal does dissipate. Or pain sensation dissipates in that area, right? Next to it, it's going to be less sensitive. Okay. That's a different type of potential. It's called creative potential. So this does not dissipate. That means it does not decay. That means it just travels as is. There is, however, something called a threshold. What do we think of thresholds? If you hear that term. Kind of like a benchmark, right? So we need the membrane potential to change to a certain amount before we'll reach a threshold. We'll talk about that. So it's all or none. Either action potential happens if we reach threshold, or it does not happen if we don't reach the threshold. Okay? What this means is in this one cell, the action potential will look exactly the same. The amount of change will be exactly the same. We'll talk about that in a second. Okay? So let's talk about threshold. So not all depolarization, that's the stimulation, by the way. We want to kind of get to a 0. Okay? So in that range, changes in that can trigger a threshold potential. And if threshold will trigger an action potential. Okay? So threshold is the voltage at which AP short for action potential is triggered. Okay? Generally, it's about 15, 20 in the depolarization range. Okay? In the typical neuron that we're going to look at, or the typical skeletal muscle we're going to look at, it's from minus 70, it's to minus 55. So let's start with that statement. Okay? So now we're going to, can I erase this? Is it okay? Information. So we can draw it again, this chart. So the next part, what we have to remember is what causes each of the changes, and what are these changes called? There's actually three phases in the action. So something causes the action potential to reach, the membrane potential to reach threshold. So in a typical skeletal muscle and typical neuron, which is the membrane potential, resting membrane potential -70, -55 is the trigger, is the threshold. At this point, sodium channels open. If sodium channels open, which direction will this flow? Up. Why? Sodium is what charge? Positive. Which direction will it move? Into the cell. So if positive charges are coming in, this membrane potential will go in that direction. So that's called the depolarization phase. I'll just write it. Right. Okay, due to influx of sodium. Okay, at this point the channel opened. Okay, so sodium kept coming in. Okay. At +30, that's the trigger for sodium channels to close. You want completion to be put here, Na channels open. Okay. At +30, Na channels are closing. Close. And potassium channels have opened. If potassium channels are open, which direction does potassium move? Out of the cell. What charge does potassium hold?
Positive.
Positive. Which direction would we now go? Downwards. We're going to lose positive charges. Okay. This is not called hyperpolarization, but it's called repolarization. We're coming back to this -70. Okay, so the second phase of action potential to 70 is repolarization phase. And it's the outward flux or efflux of potassium. Okay, losing plus charges, inside becomes less positive and okay. At -70, it's actually a trigger for sodium potassium channels to close. Trigger for potassium channels to close. But they are slow to close. Channels too close. Too close. What will that mean? They're not closed yet. Which direction will potassium move?
You're gonna have a high polarization.
Yeah,
of the
because
cell?
you're going to lose more potassium. Okay? So the third step in action potential is hyperpolarization. Hyperpolarization. Continued or continuous continued potassium efflux. And that's to about -90 millivolts. And then set back to coloristic membrane potential sodium potassium pump for each channel sodium set. And it's ready for the next potential. Next. Okay. So, changes in membrane potential, we have movement, right? So here is the animation, if you will, of the movement of ions. So here is our phospholipid, okay? Here are sodium ions, I'm showing the plus charge, just too much to write. This is negative, this is more positive, so which side is this, inside or outside the cell? Inside, more potassium inside, greater sodium outside, more negative inside, right? Here it shows channels, so this is the sodium channel, and this is for potassium. So we're going to start at minus 17, so some ions moving in, when it comes to minus 55, sodium channels open, that's here. So which way would sodium move? Into the cell, right? It's positively charged, so this minus 55 will become less and less and less. Okay? And plus 30, that's a trigger for this channel to close. Okay? At the same time, potassium channels open. Which way would potassium move? Out of the cell, we're going to lose positive charges. So from plus 30, it starts to drop. This phase is called repolarization because we're getting back to that minus 70, that resting membrane potential. Okay? And then now, the trigger for them to close is minus 70, but it's slow to close. So before it closes, a few more potassiums leak out, lots of positive charges, becomes more negative. Okay, that's the hyperpolarization phase. Okay, so this is action potential. The change of ions at each spot. Resets. So let's talk about something called the refractory period. So refractory period is another stimulus will not cause the response. Okay? This makes sure, I will talk about later, it makes sure that the impulse goes in one direction. What was the trigger for sodium channels to open? About minus 55, right? So if we have minus 55 on the way down, and we have sodium channels opening, would this go back to down to the resting membrane potential? No, it either will flatline or start to go up. Okay? So we don't want that to happen. We want to make sure that this is complete before the next stimulus or next cycle begins. Okay? This way action potential goes in one direction. So this is all to do with the sodium channel. So it remains closed, it will not open again for when the minus 55 reaches again on this way there. And this prevents another depolarization occurring before the completion. That's a refractory period, again, milliseconds. So let's talk about how, if we produce an action potential, so action potential is an exchange of ions, we produce in one spot of the neuron, how it can travel. Some neurons are half a meter long, sometimes even a meter long, depending on the heights. That's a long distance to travel. We shouldn't have to stimulate each piece. Okay? So let's imagine that this table is the plasma membrane. You're all on, let's see, you're on the outside of the cell. Let's say I'm on the inside of the cell. We're going to produce an action potential right here. What's the starting phase called? The first phase is depolarization. Why is that due to?
Sodium ions coming in.
Sodium ions are coming in, right? They're coming into this spot. What about at that spot? There is still low sodium ions. There's nothing preventing this sodium ions from moving. Diffusion is what? Passive is going to move to the concentration rate. This is zero. Some of these sodium ions move here. What's happening to the membrane potential here? It's becoming less negative or more negative? less negative, it's minus 70. Now it's going up, it hits minus 55. What will happen at this spot at minus 55? Sodium channels will open. Sodium washes in, we have that first phase starting here. Okay? This is what propagation is, self-propagated. Once we stimulate one spot, it will be its own stimulus, if you will, to make sure that the impulse travels along. So you have action potential there, here, and so on and so on. Okay? So the example I gave is of an unmyelinated fiber. Okay? What was the function of myelin? Insulation and increase the speed, right? And it was the whole neuron covered by myelin. No, what was the spaces that did not have myelin covered? Now let's use the same table. Now this is one node. Okay, let's think that spot's the next node. The myelin acts like an express train. Okay, we'll pick up the sodium and take it to that spot. What will happen to that spot then if I have gained some sodium from the inside part? With minus 70 here, what's happening? Going down. When it reaches minus 55, what's going to happen? Channels open. We have action potential here. So we have basically skipped over this much. Hence, we don't have to form an action potential in the spot. Hence, it's much faster. Okay? So those nodes are very important. We only have action potentials in those nodes. So there's a lot less action potential meaning whereas from here, this spot, this spot, this spot, this spot, and so on, if we didn't have them. Okay? So propagation is a signal, it will propagate by itself because of that local currents. Right? That sodium that came in is now high there and is lower still here. So some of it will diffuse in, triggering the action potential on this spot. Okay? So once initiated, action potential is self-propagating. Okay, in non-myelinated fibers, axon successive segments have the action potential, while in myelinated axons, where do action potentials occur? In the nodes on the side. Okay, so less action potential need to be formed, so hence faster impulse drive. Okay, it's called continuous conduction in unmyelinated fibers. It's called saltatory or skipping in a myelinated fiber. So it just occurs at the node, there's myelin sheath, occurs at the next node, and so on and so forth. That's saltatory conduction. This is in myelinated fibers. Without myelin, unmyelinated, non-myelin, it's called continuous. So each spot has to stimulate the next adjacent segment, and so on and so forth. Okay, hence this is slow. It's still relatively fast. It's still slower competitors. Any questions there? Now let's talk about how nerve cells communicate with other nerve cells. We talked about how this nerve cell has an axon terminal. It will now communicate with the next cell. Okay? This junction is called the synapse. Okay? Some synapses are electrical synapses, some are chemical synapses. At the neuromuscular junction, where the neuron met the muscle, skeletal muscle, that's a chemical synapse. Do you recall what happened at that neuromuscular junction? The acetylcholine was released. Okay? That was released from one end, it has to go to the other side, that will open some sort of a receptor that will either cause depolarization or hyperpolarization, and then the impulse can move on. Okay? So presynaptic neuron is the one before, postsynaptic is the one after. Okay? So electrical synapses are basically gap junctions. So think about that. Ions coming in, if I drill the hole, if there was another room next door, these ions move to the next cell and cause depolarization there. Okay? These are found, do we recall where? In cardiac muscles, in smooth muscles, and in our brains. So our skeletal muscles we do not. They have to do this. Okay? So it also allows what's called synchronization. That means one cell gets stimulated, all of them will have action potential will get stimulated, then all of them can contract at the same time. Okay, so it's synchronous, so you don't have to innovate each cell trying to get the heart to contract, for example. So we find this in heart muscles, in smooth muscles, even some neurons in our brain. Whereas chemical synapses will release neurotransmitters for some reason. Okay? Depending on what kind of receptors, I've erased it, right? Receptors those channels are, it can cause depolarization, sodium channels, calcium channels, right? If it was attached to a potassium channel, what's it going to do? Which way would potassium move? Out of the cell. What charge does potassium have? Positive, so losing positive charge will become hypopolarized. Right? It depends on what those channels are connected to these chemical receptors. Okay? So we either have depolarization or we can have hypopolarization, depending on those channels. Okay? When we talk about the autonomic nervous system, this is why well, look at norepinephrine. Is norepinephrine reach all of our body? Right? Yes. It flows through our blood. It's going to go through all cells in the body, right? But how come some cells, God bless you, like the heart, it's going to get stimulated, but the stomach, it will get inhibited. Same chemical, same receptor, different channels. Okay? Depending on if they open something that causes depolarization, then you have an action potential. You actually stimulate those cells. But if you get further away, is it easy for an action potential to be formed? No, it gets more difficult, right? This is how it actually works in us. This is why we kind of understand why does a norepinephrine go through all of our body. But in some organs it's going to stimulate, some it's going to inhibit. Depends on those receptors, depends on those channels of action. So here it talks about how one cell has to produce the chemical. It has a see-through and bind to a receptor, which is associated with that channel. So neurotransmitters, we have about 50 neurotransmitters. Acetylcholine is the most understood, and that was the first one we recognized. Okay, we talked about it being released in our neuromuscular junction. Some of our autonomic nervous system neurons, we'll talk about this in chapter 13. Also release them. Some central nervous system neurons release them. Right? We talked about this enzyme, acetylcholine esterase, that breaks down acetylcholine. Well, choline acetyltransferase actually puts them together. Okay, so understand that enzyme as well. As a enzyme. We do have norepinephrine, we'll talk about that when we do the autonomic nervous system. What's norepinephrine and epinephrine? Do we know if it's the same? What's the difference? Why you have different names? Maybe you heard of those two? Yeah, not sure. They're slightly different chemically, but the action is just the same. Okay. What about adrenaline? Have you heard of that? How's that different? How's that same? Epinephrine and adrenaline is the same. Just have two names. Okay. Well, there is a norepinephrine too. It's not. Okay. We'll talk a little bit more about them when we do the autonomic nervous system. We have other ones too. We have dopamine, you may have heard of We have serotonin, right? Nitric oxide, GABA. What about this endorphin? What's that? When do we release it? Come again? You can, but less often during fight or flight, but more often something else. When we exercise, okay, what is endorphin? All the sounds similar to it. It's an endogenous opioid. It's like a morphine, right? Morphines cause euphoria. This one causes euphoria, which is why as long as we exercise a little bit, we are happy. If we exercise too much, then we're starting breakdown. That's not happy. Or happy feeling. But we release endorphin as a normal response because we expect what? A little bit of tear. This is a painkiller, a natural painkiller. Okay, so when we're excited, we expect some tearing, so we release some of that to kind of to subdue that. That's endorphin. Question? Okay, we're not going to cover chapter 12 today. I think we're all tired. Let's do a little review on some of these questions. Let's talk about some common themes that people sometimes get mistaken. So, epidermis, dermis. Where are they oriented? How are they oriented? Good. So epidermis on top, dermis below. What are the two layers of the dermis? Papillary and which one's on top? Papillary. What are the 5 layers of the epidermis? Stratum basale, spinosum, next one up. Granulosum, next one up. Lucidum, and then top one, orbium, right? So which one's at the bottom again? Basal is at the bottom. So is it close to the papillary layer of dermis?
Yes.
Closest to, right? Because that's the lowermost. Papillary of dermis is the uppermost of the dermis, right? What's the functional significance of stratum basale? Mitotically active cells, that's what stem cells. Some functional significance of stratum corneum. Those are all dead cells. That's what sloughs off. Once it's corneum, it sloughs off. That's right. Lucidum, dying cells. Granulosum, yeah, keratin granules. That's got a lot of granules. That's why granulosum. Spinosum is the spine. What's the tissue making up our epidermis? Stratified squamous What is the tissue that makes up our papillary layer of dermis? Areolar connective tissue, then the reticular layer, then irregular connective tissue. Equine sweat gland. What's the function of equine sweat gland?
Do sweat pull down pressure body?
Not much, but it's to produce sweat. It cools down our body. Which one produces our natural moisturizer? Sebaceous gland. Then what's the other sweat gland that has the beard? Apocrine sweat gland. Good. Meissner corpuscle. What's the function of Meissner corpuscle? Touch reception, touch sensation. What's the one that is pressure and pain? The root hair plexus. Also touch, but how is it different? Is it the same superficial? The base of the hair follicle, so just touching the hair follicle itself. Very good. What's hair papilla? That's at the base, right? What is important about this area? blood supply to, yeah, very good, keep going. The hair matrix. What's about the hair matrix? That's where it divides the root, that's where the cells are dividing, so we need blood supply. Why do we need blood supply to hair matrix? Why do we need blood supply to stratum basale? Okay, but why from a different tissue? Which one's avascular? Okay. Epithelium is avascular, right? So even the hair matrix is also epithelial tissue. So avascular, so it comes from other connective tissues that are vascular associated. Good. That's good. What's fibrosis? Is that in tissues or skin? But how is fibrosis different from regeneration? It's other connective tissue, yep, loss of function, like our scars would be fibrosis. Right, it's lost of function. They're still live tissue, live cells, but they don't have the same function. Bone was next, right? What are the two types of bone formation? Endochondral and intramembranous, right? Frontal bone, which method did it use to form it? Intramembranous, femur, endochondral, os coxa.
That's it. Isn't that the ilium, the ischium, and the pubis bone?
Yeah,
Down
so
on the
which
lips?
method?
Um,
Intramembranous. So what group of bones uses the endochondral method? Long bones. What are some long bones?
femur,
Femur, what are
Humerus.
receptors?
ulna.
Radius ulna, yeah. Anything that's longer than wider, good. What are the other types of bone shape? Flat bones, irregular, short bones, right? All of these use which method? Intramembranous, right? Except the long bones that intramembranous. By bone tissue, we have two types histology-wise. What are the two types of bone? Compact and spongy. What is the unit of compact bone? Osteon. What's at the center of the osteon? Innervation canal. What's found within the innervation canal? Blood vessels, nerves, right? In each of those tree trunks appearing, right? What are the rings called? Lamellae, right? Are there osteocytes in them? Yes. What are the cells responsible for breaking down? Osteoclast. What makes osteo tissue extracellular matrix of bone?
Osteoclast.
Osteoblast makes the osteoclast break down. Good. What is the shaft of a long bone called? Diaphysis. What the widened out ends of long bone called? Epiphysis. What's in the medullary cavity of a dog? What kind of it? Is it red bone marrow? Yellow. Medullary cavities in the head. Where do we find red bone marrow? Flat bones. You can find it in female humors, but definitely in flat bones and irregular shaped bones. And they are within what type of bone tissue? Are they compact or spongy? Which one do we repair more often? Or easier to repair? Spongy. Let's talk about fractures. What are open fractures? Assume at least one stage to happen, right? What are the stages of repair of fractures? What's the first phase? Kind of Here it's called something else. Hematoma formation. Right? What's the next phase? Fibrocartilaginous. Another word, callus. That's the developing part. Next phase. Bony callus. What type of bone forms this? Connects these two pieces, broken bone. What type of bone tissue connects the two bones and forms a bony callus? It's the spongy bone. That's spongy bone always. And then what's the last phase called? Bone remodeling. What happens at this phase? Yeah, so wherever there should be compact, that spongy bone gets converted to compact bone. If it was spongy, what happens? Spongy just stays. If it was a medullary cavity, narrow cavity, what happens? We'll cut them out. Right? So it will represent what it was. Please remember the spongy bone actually finds it initially. Which is why, yes, after 6 weeks we should see that connection, but it's still easy to break, which is why we always say just take it slow, build it up so you don't suddenly go and break it. Good. What's a complete fracture?
All the way through.
All the way through. What's an incomplete is just like a hairline, doesn't go all the way through. Displaced fracture, is that the same? No. What's that describe? You know, the bone, the broken bones do not line up as displaced, while they are lined up as in an undisplaced fracture. Good. What's an open reduction? To do what? Yeah, so we're going to try and not only line it, but a lot of times the lining is the important bit, but also to keep it aligned. There's a reason why it didn't stay aligned, right? Whereas close reduction, some of the bone can put it together without having to open it. There will just do a class. General rule. Good. Joints, we talked about the different types of structural. What's the functional classification of joints based on? Degree of movement. What are immovable joints called? Synarthrosis. Freely movable. Diarthrosis, some movement. And arthrosis. What are the 3 types of fibrous joints? Kyphosis, sutures, syndesmosis. Excellent. Which one of these, if any, allows movement? Yeah, the syndesmosis which allows, but the other 2, does it allow any movement? No. Again, this is fibrous joints, right? What are the 2 types of cartilaginous joints? Symphysis and synchondrosis. They vary by 2 things. What are the 2 things they're different by? Go with it and then maybe you can answer my question. What makes the 2, what differentiates the 2?
One is like more cartilage.
They're both cartilage, but kind of cartilage. One is fibrocartilage while the other is hyaline cartilage. So which one is symphysis? Fibrocartilage. Where can we find 2 places where we can find symphysis joints? Pubic symphysis and intervertebral. Those are the 2. Third place we can find fibrocartilage is the revision tissue. So these are fibrocartilaginous joints. Do they allow any movement? Some movement, right? So these are amphiarthrotic fibrocartilaginous joints. What about syndesmosis? Fibrous joints that allows some, right? Synchondrosis, Hyaline cartilage, how much movement? No movement, right? Only one true synchondrosis. Which one's that one? Right, it's famous. First rib and the sternum manubrium part. That does not move the distance or the angle does not change. Split the sternum, the rib will move. It does not change the angle. Remember, what is a description or a definition of a joint? Good. Where can we find planar joints? What type of joints are planar joints? Synovial joints. Where can we find planar joints? Knees, right here. Maybe so. Where can we find? Yeah, between the carpals, right, in our wrist, but between the carpals, it doesn't allow a lot of movement, right? Between tarsals. What is the joint between humerus and the ulna? It's a hinge joint, good. What about between the ulna and the radius at the ulna? Pivot joint, where else do we find pivot joints? Plus an axis, that's our first vertebrae, so we can vertebrae. Ball and socket, nice easy one. Where do we find them?
Shoulders and hips.
Shoulders and
Yes.
hips. What's the one at the base of the thumb? Saddle. Where exactly at the base of the thumb? Between what bones? It's actually not the scaphoid, but it's the carpal. We'll talk about that second. Between carpal and metacarpal. Right? And the scaphoid is, remember, the second one. First one is between them. There's trapezium. That's the first one. That's where the saddle joint is. The base of the ellipsoidal or condyloid. Do you find them? The metacarpals, between the metacarpals and phalanges, right? So we're able to kind of circular motion as freely as our shoulders, but here we're also condyloid shoulders. What's a bursa? What kind of fluid? Synovial fluid. Is it found inside the joint? Outside of the joint. What produces synovial fluid inside our synovial? Which structure? Starts with that name. Synovial membrane, right? What is synovial membrane part of? It's our capsule. Capsule has two layers. Which one's the synovial membrane? Because it's going to produce the fluid into it. It's fibrous layer on the other side. Good. Then there's joints. Please also revise. We talked about it in lab today. Some please go over whatever we didn't get to or you forgot. Or say movements as well. Be able to describe them or pick them out if I describe them. Abduction, abduction, flexion, extension, hyperextension, and so on. That's mostly joints. Tissues. Which type of muscle tissue has only one nucleus bursa? What about skeletal? Multiple. What about cardiac? Mostly one, but sometimes two. Which one or ones are striated? Cardiac, skeletal, right? Skeletal is also striated. Where do we find cardiac muscles? In the heart, anywhere else? What about blood vessels? The walls of blood vessels, what kind of muscles? Smooth, right? So, hollow organ walls of hollow organs should be smooth. Which one's voluntary control? Skeletal. Does that mean we can't control cardiac? We just can't consciously control it. We still do control. Our brain does control it. We're still consciously control it. What is muscle tension? Force. No. How is it different from load? It's also force. Kind of passive, yes. What is tension? Beneath by the muscle, load is what's on the muscle or what's on it, which forces things in. Overcome. What is isotonic contraction? What's remaining the same? Iso means same, right? The load is the same, so the tension is also the same, right? That's isotonic. What about isometric contraction? What's same? What's not changing? Isometric. The length of the muscle. When does this happen? Yeah, so when the load exceeds the tension, right? Pushing something, trying to lift something, trying to move something heavier. Good. What is sarcolemma? What's a sarcolemma? Lemma, lamella, layer, what's the layer of this? It's the plasma membrane, it's like a layer of skin and all. It's skeletal muscle. What's the cytoplasm of skeletal muscle called? Sarcoplasm. What's the function of sarcoplasmic reticulum? So there's calcium. Let's talk about the action of the stop. What's the first stage of contraction process of muscle? So receive the stimulus, right? It's at the activation of the muscular junction. Stimulus is going to come from this side. What's going to happen in between? Chemical is going to be released, so we didn't talk about it, but that's basically what it's going to do, right? We talked about in there how when acetylcholine binds to a receptor, it allows sodium to come into the cell, right? The sodium comes in, and then we get action potential in the muscle. Okay? That's the first stage of action, activation. What's the second phase called? Excitation, contraction, coupling. That's the premise of it, about what's happening. We have this impulse going, but how does it translate? What's released? Calcium is going to be released in the sarcoplasm. What does this calcium do when it's in the sarcoplasm? Binds to troponin, then changes shape. What happens when it changes shape? Moves what away? Yeah, so what moves away? Tropomyosin moves away and exposing the actin's active site, and then the myosin head burn into it. Then the next one is called phosphate cycling, and binding, movement, unbinding, rebinding, spot, movement, and so on. Right? How do we terminate contraction? We do a couple of things. We have to remove the acetylcholine in the neuromuscular junction. Which enzyme does that? Acetylcholine esterase, yep, that breaks down acetylcholine. One more thing we need to do. We need ATP for two things. Myosin head, we need ATP to unbind it in the actin. We also need ATP for one more. So what triggered the excitation contraction coupling? Actin came, and what did it do? Calcium was released, right? So we need to take the calcium back. We talked about rigor mortis here, right? Somebody came and asked me last time about acetylcholine esterase, sarin gas. You heard Saddam Hussein used it against people there. That blocked acetylcholine esterase. Okay, so initially they would not die, but you watched or seen images of them. What did they remain in? So if I am not having any acetylcholine esterase, what might it look like? Rigid. They were actually rigid because they could not relax. Right? They were still alive, but they were in the contracted muscles to boost the injury die. Right? And that's why, because the sarin gas blocks the acetylcholine esterase. So we need both of those to happen. We need to remove acetylcholine, and we need to disconnect as well as remove the calcium, because if we don't remove calcium, what will happen? Or what's calcium inside muscle cell doing again? Yeah, binding the troponin, keeping that active site visible, right? If we take the calcium away, troponin changes shape, tropomyosin covers that active site, myosin. Okay. It's part of our relaxation process. Any questions? Also review the structure of the sarcomere, like A band, I band, what makes it up, what happens during contraction. What is a sarcomere? Structural unit of muscle. Of what part of the muscle cell, by the way? Of that structure that we have, sarcomere, the sarcomere. Not the muscle fiber itself, yes, it's found within. Myofibril, yeah, myofibril, that is the contractile organ of filaments. Filaments are the actin, thick filaments, thin filaments, they are inside. So review that as well. What happens during contraction? Questions? Have a wonderful day.